Critical Timing and Synchronization, hosted by Orolia. My name is John Fisher, and I'm the VP of Advanced R&D here at Orolia. We are also fortunate to be joined by 3 other excellent speakers today. Mr. Francisco Girela, Responsible Technologist for the Americas at 7 Solutions. Mr. Roger Hosking, Vice President for Pentech. And Mr. Hiro Sasaki, President of Orolia Defense and Security. Before we get started, I would like to, I should have shown you the pictures of our speakers as well. But before we get started, we have a few housekeeping things to cover. This webinar is being recorded. For those who are unable to join us live today, you'll be able to listen to the recordings. We encourage you to submit questions during the meeting and throughout the question panel. We had also received some questions when you registered, so we've prepared to cover those as well as any other ones you might have. We'll answer as many questions as we can during the Q&A session towards the end of the meeting. If for some reason you lose a connection to the meeting, you can join again using the same meeting link. Our agenda today includes presentations from, let's see, there's the housekeeping. Let me move on. Here's our agenda. The agenda for today includes presentations from each of our speakers. I'll start off with a quick overview to orient you on the subject, and then Francisco will present the White Rabbit synchronization for complex mission systems, followed by Roger, who will discuss critical timing for defense applications, and then Hiro will share information about resilient and stable time sync for military applications from Orolia Defense and Security. And then at the end, we'll finish up with question and answer session and the next steps. So it's an interesting event we have, but before we start, let's start with a quick poll thing. Sherry, can you launch a poll? Okay. So in which sector do you operate? These are just very general defense and security, critical infrastructure, so anything telecom, power, anything like that. Transportation, this would include automotive, rail, aviation too, if you're working that sector, or other. And this will give us an idea of where your interests lie. So please select all that apply. You can select more than one in the areas of where your interest is. We'll wait for those results. And okay, excellent. We have a big group in defense and security, and others in the other area. Okay, great. Then this will be a good lead-in, and I think we'll get started. I'll go over with an overview, which you need to go back. An overview. So again, it sounds like a majority of the audience already works in defense and security, and so they are familiar with what we call the C5ISR picture. So command and control, intelligence, surveillance, reconnaissance, and which is all being done under adverse conditions. In a military environment, we have what we call electronic warfare. And what neat is you have all these sensors gathering information, putting them on a network. Network users are using this information, and that all needs to be synchronized to create a common picture. So that's a big area of defense synchronization. But that's at a high level. At the next more detailed level, these sensors are, instead of operating individually, can operate as a group in concert with each other, and they need to optimize their accuracy, to optimize their resolution. They need synchronization among themselves, like sensors, like things like that. And so you'll be hearing from a number of the speakers about that. So just to give you the context of what's going to be talked about, you have that bit of overview. So now, I guess, now that we have that, I will continue on. And Francisco, I will turn it over to you. Please take it away.
Hello, thank you, John, for the introduction. I'm Francisco Quirela, lead technologist at Seven Solutions, and I will speak today about white rabbit synchronization for complex missions. So, first of all, I would like to introduce the white rabbit technology. White rabbit is an ultra-accurate implementation of the standard PTP time synchronization protocol. And its main characteristic is that it is able to achieve sub-nanosecond accuracy. Thanks to the fact that this technology is based in the standard PTP, it is easy to integrate in Ethernet networks, and it is also interoperable with different time synchronization protocols or mechanisms like NTP, like PTP version 2, or pulse per second distribution and clock distribution. The good thing about this technology is that it is a time distribution technology, and this means that as we are distributing the time using a physical interface, in this case optical fiber, we are resilient to GNSS disruptions. Thanks to the implementation of the technology, we can save some of the calibrations and the complexness of the deployment that when we are using other time synchronization techniques, and we are able to scale to thousands of nodes in metro areas. White rabbit has been used as the reference for the new high accuracy profile in the latest revision of PTP version 2.1 that was released last year. So benefits about this technology is that it is able to provide sub-nanosecond time synchronization accuracy in links from a few feet to several miles without any kind of calibration, and it is also to distribute frequency with a phase noise jitter below the 1 picosecond level, including some compensation of the temperature excursion that we see in the link. Thanks to this, white rabbit is able to provide different frequencies that you can program. It can provide triggers, it can provide a time reference, and it is also able to provide data with a deterministic latency in the link. White rabbit can be deployed using different topologies, ring or star topology, including several hubs, so we are able to deploy resilient time synchronization networks. And as I mentioned before, we can distribute data and command using the same links without affecting the performance of the time synchronization. As we are able to deal with data, we can be an interface to general purpose data management switches or routers using the Ethernet link. The white rabbit devices are managed and monitored the same way that any other networking equipment, so they are easy to deploy, and also provide failover mechanisms and time error detection features. So they can jump from one reference to the other in case of failure, or they can jump in to an internal rollover oscillator that they have embedded. The devices are already calibrated, so you don't need to take care of fixing these small asymmetries, and you just need to plug the devices and they will start synchronizing with this nanosecond accuracy. And as its synchronization is based on optical fibers and can handle also the data transmission, you can reduce the cabling and also the associated weight. The typical topology for a white rabbit network will be this. In this case, we use the white rabbit devices to distribute a local or an external time reference, in this case provided by the Orolia Secure Sync, using optical networks to the end users that need to consume the time information because they need triggers or because they want to timestamp different events. And at the same time, we can deal with data transmission from the end users to the central processing unit, or from the central processing unit to the end user. Some examples of the use of this technology will be the SDR synchronization for ultra-low frequency antennas or phase array antennas or elevators. In this case, the case number one will be using White Rabbit devices that have multiple outputs, analog outputs, pulse per second or clock outputs to synchronize the different SDR. Or in the case two, what we can do is to embed White Rabbit hardware in each one of the different SDR modules that we have connected. A third option, which is actually available for some SDR, commercial SDR, is to integrate White Rabbit capabilities inside the same device. And this not only applies to SDR, it also applies to any other device which is based on an FPGA that can host the White Rabbit core that we use to synchronize using these nanosecond amperes. Additional examples is the distributed data acquisition that we do, for example, in the Cherenkov telescope array. In this case, we timestamp all the information that different telescopes are receiving, and we send triggers. And at the same time, we deal with the data aggregation and the packet routing in the network. A second example will be radio over Ethernet for time and frequency dissemination that we do in the square kilometer array. In this case, we have hundreds of antennas distributed in an area around 65 miles, which are connected using optical fiber hanging in the air, as you can see in the second picture. So in this case, we tested both the time synchronization and the frequency distribution. In the case of the frequency distribution, you can see that the jitter is below 1.8 picoseconds after 3 hops. And in the case of the time synchronization, you can see how we compensate for the temperature excursion that we are feeling, and we still maintain this high accuracy time synchronization. Another application will be the use of time synchronization for terrestrial GPS. In this case, what we do is to synchronize the ground stations that are the one responsible of the triangulation of the signal. We can do that using wireless links, but what we propose is to do that using wired link and the White Rabbit technology. Once that the ground stations are synchronized, then we can work as a GPS, providing information to the different tags that need to be positioned, or we can use the tags as a reference point to the ground stations and calculate the positioning and navigation information in the ground segment. The benefits of having this time synchronization using wired links is the extension of the coverage, and because you don't need to communicate between the different ground stations using the wireless link, and this way we can have an area of interest which is a little bit more distant to the ground stations. Additionally, as we are distributing timing using a physical link, we avoid disruptions on the wireless link, and we can use the frequency distribution of White Rabbit to improve the spectrum utilization that we are doing in adjacent cells, reducing, for example, the guard bands that we are using in each one of the ground stations. One example that we did was to check the coverage that we had with a terrestrial GPS based on ultra-wideband, and at the end, what we obtained is that we are able to position with an accuracy in the level of around 8 inches, and we can extend the coverage at 75% compared to the wireless solution, even in scenarios where we have inhibitors in place. In this case, we did a test near a police station that had one inhibitor, and we were able to synchronize as well. One last example that I would like to remark was here. It's an experiment that was published inside GNSS, where they perform code and phase ranging and performance analysis. What they did was to localize an UAV in real time through a synchronized network of ground stations. And thanks to the fact that they synchronized the ground station, they avoided to have an atomic clock or a very stable time reference in the UAV, saving cuts or cutting the cost of the experiment itself. This has been all from me. Now I think that I will leave John to have another poll question.
Thank you, Francisco. That's just fascinating. It's amazing the accuracy you're achieving there. And for years, I thought we were doing well when we had nanosecond type accuracy, and you're working in picosecond level. That's impressive. So before we start with our next speaker, I'd like to do another poll question. So prior to this webinar, have you ever heard of White Rabbit technology? So if you could just select one and let us know. As you said, that this technology that you just heard about from Francisco is, I guess the official name is PTP high accuracy. It's a special method in PTP, the precise time protocol over Ethernet, but it's colloquially we've adopted the phrase White Rabbit. So have you ever heard of that before? And so we're going to look at the results here. Okay, so a few of you have, but it sounds like some of you know it a little bit, and about half have never heard of it before. So I'm glad you joined. Glad you had a chance to hear that, because that, I think, is really a technology for the future. So with that, Roger, I'll turn it over to you.
All right, thank you very much, John, and thank you everyone for joining today. We hope to have a interesting and informative session with you. Pentec, as you may know, is a COTS vendor, primarily in the defense community. We've been in business for over 30 years, delivering high-speed data acquisition, radars, communications, SIGINT solutions to the military. And we use precision PNT timing and GPS in almost all of our applications. They include mission signal recording systems, where we record wideband RF and IF signals, multi-static radar systems, and also passive multi-static radar systems, which we'll take a look at very quickly. And then satellite tracking and recording using our recorders. We also are selling into applications such as electronic warfare and countermeasures, which I won't get into the details today. Most of these are pretty classified, and so we'll skip over those. I think the principles, though, that we'll illustrate today will give you an idea of what can be done with COTS hardware in this market. So we'll start with airborne mission signal recording systems. Here, what we do is we digitize radio frequency signals. They could be radar, they could be communications, and we store them in a RAID array in real time. So we have A to D converters and front-end receivers that will capture and then digitize and then record. But we use GPS and PNT stamps to be recorded in parallel with the data recording. We are extracting a 10 megahertz reference signal from the GPS. And that is used to synchronize our sampling clocks in our A to D converters and D to A converters, so that as time goes on, that synchronization with GPS timing will ensure that all of the samples are laid down in a very well-ordered time, and the timestamps that are recorded will then be aligned perfectly with the real time in our recording, because the timestamping and the synchronization again are all synchronized. So you can set programmable intervals for your timestamping. You can pick 100 milliseconds or 1 second or 10 seconds, and each time that tick occurs, you will be logging in your GPS time, the latitude, longitude, and altitude of the particular airborne recorder, along with the data path. So it allows you to reconstruct the flight path and everything that was received in its path. The next example is a multi-static surface ship radar system. This was developed by one of our customers, University of Cape Town, South Africa. It's a dual band, dual polarization, multi-static radar system called NextRAD. It's designed, and the hard part of it was to eliminate sea clutter for maritime radar targets. A multi-static configuration, we have one transmit and receive node that is the only active transmitter, and then two receivers, which are passive receivers to receive reflected signals sent out by the transmitter. The benefits is that you can reduce noise by having multiple receivers, you can improve your detection range and identification, and of course, you can have the triangulation benefit of 3 different receive sites to triangulate and pinpoint your target more accurately. So the way it works is the trigger is coming from a GPS receiver. Typically, we use the 1 PPS hardware signal that generates an outgoing pulse from the transmitter. And then the reflected signals are acquired synchronously after that trigger in a range gate that we generate from, again, from that same trigger. These receivers, of course, are at different locations, but each one of them has a GPS receiver to allow synchronization across the multiple receive channels. So you perform some Doppler signal processing within each of those receive stations, and then send the results for aggregation to a central facility for doing the signal processing to solve the solution for absolute velocity, direction of travel, position, azimuth, and elevation. An example of a passive multi-static radar using commercial UHF transmitter. This is something that's becoming popular in both in commercial and in military. What you do is you kind of hijack a commercial transmitter, like a TV station or a radio station, and then you use the reflections from the signal from that commercial transmit signal to different receiver stations to do the triangulation by sending the results to a central facility, very much like in the previous one, where you're then able to extract information about the target. So in this one example, the transmitter is KTLA, which is a major TV station, channel 31 in the LA area, a megawatt of power. It's high, it's 3,100 feet, 10 feet high, and very good reception. So there are 3 receiving stations located in the area at Malibu, Catalina Island, and Dana Point. So the benefits here is that there is no detection possible. This is a commercial transmitter, and so these radar systems can be completely non-detectable. You don't need licensing, and it also allows you, in case of an outage, to switch to a different transmit source, which helps you avoid jamming and other disruptions. So it's quite a nice technology. Again, everything in those 3 stations, of course, are synchronized using GPS receivers, so that the acquisition range gate for each of those signals can be synchronized, as well as the sampling rates. We also use GPS in our recording systems to track a satellite from different geographic ground stations, and this is quite popular because of the features of we have a time like a time alarm clock recording feature in our recorders. You can set it to GPS time to acquire signals precisely at the same clock tick, synchronized through GPS with the trigger signal again coming from the PPS signal, sampling rates coming again from the 10 megahertz reference. So it allows you to do, again, the triangulation on a much larger scale to track a satellite. This really also, by having multiple antennas, improves diversity receiving so that you can kind of average and aggregate the dynamic range effects by having multiple antennas receive signals from the same target. And this allows you to check up on satellite constellations, make sure that they're in the right place. You can detect new or unknown or satellites that could be military or defense intelligence targets. So the thing that kind of ties all this together is that how do you do it exactly? How do you transmit the timestamp, the PNT information around within your system? And we're currently using VITA-49, which is the radio transport protocol, often called VRT, which we've been working on since the beginning, and we're very instrumental in evolving this standard. It's really a way of transmitting timestamps across a network, distributed network, to different entities, different stations on the network to share timestamp information in the packet that's aligned really with the packets of data that go out to be distributed for processing. So for example, you could have in this picture at the right, you have 4 different radios, each receiving a different signal. They could be the same or different. The signals are timestamped, sent across a network switch using COTS, like gigabit Ethernet or 100 or 40 or gigabit Ethernet signals that then are distributed through a switch to different consumers of that information, who then process the data, the same data, with different algorithms to extract the information that they need for their particular area of interest. This VITA-49 has been adopted by popular industry standards and is being used extensively in the mil, aero, and defense space. Also, there's another standard, SOSA, Sensor Open Systems Architecture. After all, radio antennas are sensors. This is a major initiative, tri-service support on the US DoD. What it does is it standardizes specific subsets and extensions of OpenVPX hardware, but it also uses the VITA-49 as its protocol for moving time-stamped data and metadata around the different system resources. So this gives you some really nice interoperability by using a standard way of distributing data and timestamping. And this gives the government less expensive upgrades, and it simplifies its new technology insertion, which is very, very important to our military. So just to summarize, we've been using GPS receivers, timing generators for over 25 years, and we've been benefiting from the vendors who are supplying solutions like the ones you're hearing from today to make our products perform better, to get better accuracy, better precision in terms of location and timing, which is especially critical for so many applications that we do. We have built the synchronization and timing features into our products so that they are easy to use by customers. They're ready to receive the reference signals and the trigger and the PPS signals. And we have software and hardware features that take advantage of those signals, and often it's an integral part of the solution. So these services, the PNT services, are really becoming increasingly important. And also now in the evolving artificial intelligence, machine learning initiatives, these are very globally strategic technologies where PNT plays a very critical role that'll be more important in the future. If you'd like some more information about our products, you can go to our website. We've got lots of information there. And I really do appreciate your attending this section today. Thank you very much. I'll turn it back over to you, John.
Thank you, Roger. That was fascinating. Your application of passive radars in a civilian application was particularly interesting for me. I think, as you said, most of our audience we saw was military. We know that passive radars are used not to on the battlefield to avoid transmitting because you become a target, right? But that was an interesting
Exactly.
you showed there in the civilian world. That's great. Well, thanks. So before we go to our next speaker, we have another poll question. This one is, as Roger had mentioned, there's a lot of standards and they've been following. One of them being the Open VPX standard. And so we want to ask you just to select one of these. Are you using Open VPX in your system? Yes, for military applications, as Roger mentioned, there's SOSA, CMOS, all of the military have adopted and falling into those VITA standards. Or yes, commercial applications, or no, not at this time. So if you could just choose one of those, whichever, if you do more than one, just choose the one that you do the most. And maybe we get a feeling for how well these standards are being adopted. So we have our results. So it looks like about a third of you are, yes, you're doing for military applications. I know that's something we're jumping into. Not much in the commercial area. Okay, that's new to me. And then about 2/3 are not doing it at this time. So, all right, well, great. Good information there. And so now, Hiro, I'll turn it over to you.
Good morning, John. Thanks for the invitation to present today. I think we have a global audience, so good morning, good afternoon, and good evening to everybody, wherever you may be. I'd like to use the time today to focus on talking about time synchronization for military applications. And of course, since we're talking military applications, we want resilient time. But I want to spend a little extra focus today on time stability. And I want to talk about why time stability is really critical for military applications. And it's an area that I think, over the years, we've been fortunate at Orolia to be able to support some significant different military applications with time synchronization capability. And we've learned a lot of ways to do things that might not come intuitively. It could be something that you're all aware of normally working in this area, but I think it's an important area that sometimes doesn't get enough focus, and I'd like to kind of raise the attention on that a little bit. I'd like to go back to a diagram that John had presented earlier, encompassing the C5ISR and EW systems. And when we look at this, at a high level, it might not look like timing is critical for every aspect, but I want to point out some areas where it is extremely critical. Precision time and synchronization in command and control applications. So when we have better time synchronization, we'll have improved situational awareness. We'll have the ability to provide improved data correlation, which allows for better decision making. And additionally, we have improved navigation, so we have a better sense of where everybody is at any given moment, where all the assets are. And I think we heard some examples from the previous presenters as well on how their technologies can improve the whole system design as well. In communications, if we have better time synchronization, we're going to have higher jamming resistance. We'll have better radio communication waveforms. We can support waveforms that provide longer radio silence that don't require over-the-air resynchronization as often. In communications, we can also provide detection of smaller targets. I'm sorry, that's probably for my radar applications there. But in communications, we can provide improved security. So by having better time synchronization, we can use better encryption protocols as well over the air. And in radar and missile defense systems, this is probably an area that we've heard already from the previous presenters, that radar is a key capability for the military, and precision time synchronization is extremely important. But we have a higher probability of detection when we have better time synchronization. We have longer range detection when we have better time synchronization, and we can also detect smaller targets. So all of these capabilities improve across the board when we have more accurate time synchronization across our different network nodes. When a lot of these systems were originally designed and developed, modern systems that are in use now and fielded now, there was an assumption that GPS signals would always be available. And that assumption led to certain system designs that don't typically survive in more challenged environments. And so when we remove that assumption, there's an immediate need for backup systems. Now, many of you are probably aware there's lots of effort and lots of research and development going into providing access to good time references when we don't have GPS, or ways to mitigate the threats against GPS. And so some examples here, of course, we have different types of encrypted GNSS signals, SASM and PRS being different examples out there. Different ways to provide anti-jamming capability with smart antennas and SERPA antennas. Additionally, we can look at augmentation signals, other types of signals that are out there that we can use to track position or changes in position. There's other wireless systems out there as well. And then what we heard earlier in the White Rabbit presentation as well is, different ways to provide time transfer remotely and transfer time between nodes really effectively. And then also, there's lots of different types of atomic clock technology that we can use to provide holdover when we don't have time from GPS. So that's all great, and lots of focus there, so I won't spend a lot of time on that. But I'd like to drill down a little bit on stability of time. The graphic here is pretty straightforward, simple graphic, but we're talking about stable time and not necessarily just accurate time. And the goal should be stable and accurate, but sometimes we forget about stability when we're achieving accuracy. So I really want to highlight the third chart there that says accurate but not stable. And that kind of illustrates what I'm talking about here, that there could be variations in time. On average, provides accuracy, but at any given point is not stable. So there's some simple approaches to providing stability with GPS, and what that has resulted in some issues with downstream systems. And I've seen this firsthand. We've seen this firsthand with some of our systems that we've integrated into, where when GPS is not available, there's a hard switch over to some other time reference. It creates discontinuities in time. We get oscillators that snap to different time sources, and all of this also increases the overall phase noise, the noise in the system on time stability. And those type of effects can cause many issues with downstream systems. I mean, that could potentially take down an entire radar platform if there's an issue with the time stability. So maybe these are no longer GPS disciplined oscillators, GPSDOs, which is a common acronym in the military applications. So maybe there's a new acronym that needs to emerge, maybe something like PNT disciplined oscillators, position navigation and timing disciplined oscillators. So stability with multiple references, it's not a technically challenging problem to address, especially in a lab setting, right? In a lab setting, equipment's there, it's very stable, environment's very controlled, and we can do different things to provide time stability with multiple sources. And so a couple of examples here is we can use some basic algorithms to smooth the transitions. So let's say we're going from a GPS signal and then GPS is no longer available and we're switching to a network time. We can gradually smooth the transition if those two time sources are not perfectly aligned. Another way, maybe better way to do it in some applications, is to use different types of blending algorithms. A Kalman filter would be an example, where we can continuously blend different time sources to provide a single stable time source. And there's a number of other well-documented and researched ways to do this, including different types of voting algorithms with multiple sources. But at the end of the day, the goal would be to provide a single stable clock reference. So that's great when you're in a lab environment. It's relatively easy to model, simulate, design, and develop. But achieving time stability is extremely challenging once you go into a military environment. So in a military environment, all of your assumptions about the stable environment go away, which affects the stability of your time source. And so there's a few areas that we really have to focus on addressing and make sure that we're not being disrupted by the environment. And so some of the examples of environmental effects that we'd want to minimize, it could be shadowing of the GPS or GNSS signals, or moving, in between tall buildings or mountains, or even shadowing from wings of an airplane could cause blockages and outages of GPS. We have vibrations. So as soon as you get onto a platform with an engine or some kind of propeller, you're going to have different types of vibrations. And the different frequency of rotation will affect the performance of your different time sources as well in different ways. We could have rapid temperature changes. So imagine an aircraft going from sea level in the desert up to a high altitude. You're going to experience some pretty quick temperature changes in that environment. We'll have noise from lots of other electronics. So on board these systems, especially the C5 ISR and EW systems, we're going to have numerous electronics. And that could induce electromagnetic noise. And also, once we get into space-based applications, you could have radiation effects as well that could affect your clocks. And so on top of just the environmental effects, in a military environment, we also have adversarial effects. And these could be intentional active denial of signals. It could be intentional injection of noise or false signals. And so the mitigation of those has to be approached in a different way. But also, when we start to think about how we're feeding in different sources into our system, there should be consideration on how much we trust each individual source before we factor that into our overall time solution. And so, I'm not presenting any specific answers. I think the key thing here is it requires some analysis based on the platform that's intended for use. Okay, so that's great. Now we've solved, hopefully, figuring out how to get access and accuracy from time sources. We figured out how to stabilize and provide a single stable time source. But we also have to get the time signal out to all of the electronics that need it. And the two presentations before this were great examples of how we can attack the distribution problem, right? So we've got a good time source, and now we got to get it out to all of our systems. There's lots of different ways to do this, but one of the considerations from a system design perspective is looking at the difference between adding more oscillators and more clocks and more PNT DOs, as I mentioned earlier, versus increasing the amount of distribution in the overall system. And there's definitely a cost-benefit analysis here, and it should be at a platform by platform or system by system basis. Every system is going to be a little bit different, and as the cost of time sources decreases and the cost of distribution of time sources also decreases, that could be a changing equation. And we should continue to kind of monitor how the technologies change and what's the most optimal way to deploy the technology. So in summary, I'm not diminishing the importance of ensuring availability of precision time, right? That is the whole system design, and resilient PNT starts with good time sources and making sure that those are available. But that accuracy and access is really just one step in developing a fully resilient time synchronization capability. And focusing on time stability is an area that I think is sometimes underappreciated, and especially in providing time stability through military and tactical environments that could be changing at a moment's notice is really critical to providing good military time synchronization for overall battlefield superiority. Okay, John, I think that's all for my slides there. I will pass it back to you.
Great, great. Thank you, Hero. I really like your idea about that acronym, that new acronym, a PNT-DO. I mean, I think, as you said, a GPS-DO, disciplined oscillator, is kind of now an obsolete concept. We really need much more than that. And of course, the military needs another acronym because they don't have enough. So that's a great idea. So thank you. Okay, well, we're now our question and answer period. But before we do that, we have our one last poll question. So please answer this. Would you like someone from Orolia to contact you after this webinar? So simple yes or no. We don't have to wait around for the results. You can go ahead. This will be up, and you can answer for the rest of our webinar here. So just please give an answer if you'd like that. So I think then we'll go into our question and answer round. Let's start with our first one we had from our registration group. First question I have is it time to move away from GNSS for primary time and frequency and use network protocols like PTP instead? So Francisco, how about you? Maybe that's in your area. Would you like to answer that one?
Yep, sure. So I would love that, yes, because we are network time synchronization manufacturers. But the reality is that at the end of the day, unless you want to have a local reference, you still need an absolute time reference or a time scale. And the only way to retrieve this time scale right now is using GNSS-based systems, or having access to the atomic clocks of the national metrology institutes that maintain the time in each country. So I don't think that it is a matter of replacing it, but complementing it with different technologies.
Yes, yeah, that makes sense. Anyone else? Anyone else like to add a comment to that?
Okay, John, I'll comment if that's okay. Yeah,
Sure.
I completely agree with Francisco as well. And I think, in addition to that, I think diversity is important, especially for military applications. So I don't think there's a single technology that's going to solve all the problems. And so I think it's important to make sure that we're looking at ways to combine different technologies to provide a more resilient solution overall.
Yeah, good point. As many people say, there's no magic bullet here, so we need a lot. Yeah. Next question. Do we need to actively manage the fact that clocks are improving faster than systems that they are embedded in? Roger, maybe you might have something on that one?
Sure. One of the problems we have in building systems is clock distribution to the different system elements, and not do anything to degrade that clock that's say measurable or of a degrading way is often very difficult. And this has to do with synchronizing multiple boards in a system, multiple chassis in a system, and even across optical links because now more and more we're using optical connections between different elements of a system. And so what I think that the goal should be, and as the clock accuracy and the precision and the stability, all those critical factors improves, you have to make sure that those distribution methods that you use don't degrade it beyond the required precision of your application system. And that might take some work, but if the benefits of having that improved accuracy are part of your application's objectives, then that's very important to do that. So we typically take the 10 megahertz reference and use that as a frequency reference standard for our frequency synthesizers to generate high-speed gigahertz frequency sampling clocks. We have to be very careful in phase noise and other characteristics, short-term and long-term stability, to make sure that we do that job extremely well. So it's a combination of distribution and synthesis, frequency synthesis, to create our sampling clocks. That has to be done very carefully. And if the time source improves, we need to try to keep up with that so that we can take advantage of that improvement.
Great, makes sense. Hiro, Francisco, anything you'd like to add to that?
Sure, John. Yeah, I'll comment on that. I think I'll piggyback a little bit on one aspect that Roger had presented as well, about standardization, industry standardization, and specifically the SOSA and CMOS capabilities. I think when we look at that, what part of the goal of those type of industry standards is to create a modular approach for different technology subsets. So for example, we could provide PNT or timing on a slice that goes into a system, and that slice for PNT could evolve at a different pace, different cadence than the other electronics that are on board the system. And so on the other hand, Roger and Pentec and the stuff that they've done there is really impressive, and they're able to innovate on the different types of EW and RF capture capability at a different cadence that's independent of the PNT solution. And as Roger mentioned, as long as we standardize and agree on the interfaces between the capability sets, then we can hopefully work with the military organizations to keep up to the pace of the technology development in the industry.
Yeah, just one other point on the standards that are evolving. Recently, OpenVPX initiated a radio clock distribution backplane scenario where clocks are sent from a central timing board independently to each of the slots of the OpenVPX chassis, which does a lot to improve that clock distribution problem I was talking about before. And now that has become part of the SOSA standard, for example. And so, we are paying attention to it, and the industry is, because it's important to the customer. So anyway.
Great. Okay. I'll move on to the next question. This person is interested in a discussion about the relative or closed system accuracy of an ultra-high precise synchronization system over seconds or minutes. So I don't know, Francisco, would you have a comment on that one?
Yeah, sure. So here the first thing that we need to discern is if you are distributing a local reference or if you are using an absolute external time reference. Because in some cases, if you are using just a local reference, you don't really care that much about the drift that you have to an external absolute reference. And in those cases, you can maintain a very good relative timing between all the different parts of your system, just using a distribution or distribution technology. However, in many cases, you will need an absolute time reference. For example, as we spoke before about a GPS reference. And in those cases, the only alternatives that you have is first jumping to a backup source, or second, jumping to an stable internal source that you discipline to the external source. That will be the case of holdover oscillators like Rubidiums or CSATs. And there are many implementations. If you care about the seconds or the minutes time frame, in those cases, there are different oscillators that are able to provide nanosecond level time synchronization, even in holdover conditions. Problems might arise, of course, when you have vibrations or you have movement in the oscillators that could degrade a little bit the holdover capabilities. But typical values for these kind of oscillators will be having single to tens of nanoseconds in the first minutes after losing any kind of reference.
Great, yeah, makes sense. And as you pointed out, this idea of a holdover oscillator kind of thing there, that is, we have a whole division at Orolia that works on that thing there. And maybe just to point out to the audience that what we think of like atomic clocks of being very exotic and really giving you that nanosecond accuracy even over hours and time. They're no longer exotic devices, and they're affordable, they're smaller. Last year we announced a small affordable atomic clock, which is a drop-in replacement for an OCXO. So if you're thinking atomic clocks are too exotic, don't think that anymore. Things have evolved. So great. I'll move on to other questions. Actually, we have a number of questions asking about alternative techniques to GPS, and what do you do about jamming and spoofing, and how do you harden your system to these threats. I'm going to skip over those now because we only have a couple more minutes left, and just maybe to point out to the audience, if you have those, we've had a number of webinars in the last several months on those topics. So if you look at our website, you can listen to the playback of those things and probably learn a lot. So in just a minute, I think I maybe have time for one more. This question is there a demand, theoretical or practical use for more precise time measurements? For example, nano, pico, and do you foresee any limit on this accuracy? So I'll call this a toss-up question. Anyone want to jump in and respond to that?
Hey, John, I'll comment.
Jump ball, so go ahead. Yeah, go ahead. Go ahead, Hero.
Okay, thanks, John. Yeah, sorry about that. Yeah, maybe just a quick comment. I think what I heard was the question about precise time measurement. So what I would say, and it's definitely not an area of expertise for me, but what I would say is precise time measurement needs to be always better than the time that we're trying to deliver, the time accuracy we're trying to deliver. And so we need the measurement devices to stay ahead of the capabilities that our customers are asking for to be fielded. And I know that becomes really challenging, especially when we start to measure in picoseconds as well. So it's kind of a request to industry maybe from me.
Yes.
Yeah, to complement the Hiro's answer, I think that we have no limits. Every time that we think that we have reached a limit, we go beyond it. So I wouldn't say that this is something coming any moment soon. It's true that we have new technologies that fulfill current requirements, and some of them even are slightly overkill for some applications. But with the trend that we are seeing at this moment of more communication, more wireless links being deployed, especially in metro areas, the automatization of, for example, driving or transportation, what I will expect is to have more stringent conditions to operate, and this will lead to an increasement or to an increased requirement of better timing and frequency too.
This is Roger. I would say that generally our customers are much more concerned with relative timing between the channels than the absolute time, particularly in large phased array antenna systems, which are really pervasive in the defense and radar especially. So while it's nice to have precise absolute time, the relative time between elements and antenna elements is really the driving factor for us.
Yes, and that is a really good point. He says this phase array, and picosecond, especially, you know, if you're talking about as we move up in frequency, picosecond level relative timing is needed. So I don't think there is any end in sight. We need higher accuracy. Like everything else, it's never enough. So, okay, we're at the top of the hour. I think we have time for today. So let's. I think these were great questions. I think we have some next steps here. Yes. So we will be having another one in another one of these webinars in February. So look for details in your email on that soon. Our emails are here if anybody wants to contact us. You got any more questions or even want to keep the dialogue going? I want to thank the speakers, Francisco, Roger, Hero. Fascinating presentations you've done. Thank you. And thank you, audience. We look forward to seeing you at the next Coffee Talk. Thank you.